last topic, and that is consistency and uniqueness. So a system is consistent if it has at least one solution. Oops, I missed an S here. That's the definition of consistent. And if it has only one solution, it's called unique. These are not tricky terms here. They're very straightforward. All right, so let's look at a couple systems and talk about whether they are consistent / unique. So we'll consider the systems from example 1. Point 1. So the first system, if we wrote it as an augmented matrix, would look like this. So if we just go back real quick, you can see that I'm just taking the numbers from this. Oops, I messed up. The last number here is a 2. So, and if we did row operations on this, I claim that we'll get 1, 0, 1, and 0, 1, 1. Okay, that's x1 equals 1, and x2 equals 1. We saw that by looking at the intersections of the lines, but we can also do this algebraically. And this is unique. There's only one solution. It's the point 1, 1. And consistent. All right, let's look at the second example. So that was 1, -1, 0, 1, -1, 1, 1. And if we do row operations on this, we'll get 1, -1, 0, and 0, 0, 1. Okay, now this is going to produce two equations. It's x1 minus x2 equals 0, or x1 equals x2. And the last equation says 0 equals 1. That's a problem. That's not allowed in math. So this is not consistent. There's no solution. This system doesn't make sense. You can't have both these equations be true for a particular pair of numbers, x1, x2. And you could say this is inconsistent or it's not consistent. All right, and then the last system from earlier was this one, -1, 0, 1, -1, -1, 1, and then 0, 0 is the last column. And if we row reduce this, we would get 1, -1, 0, 0, 0, 0. And this just gets us x1 equals x2, and then 0 equals 0, which is always true. So this is consistent. There are points here, but it's not unique because there's many pairs of numbers, pairs where the first and the second number are the same. All right, last example, then we'll be done. Let's consider a system with a parameter. Oops, I got to write the system and then I'll write the matrix. So the system is going to be x1 plus 3, x2 equals 3, and 2x1 plus hx2 equals 4. So we're going to put this in our augmented matrix form. So 1, 3, 3, 2, h4, and we're going to augment it, or not augment it, row reduce it, do row operations. So we're going to take the first column, multiply by -2, and add it to the second column. So negative 2r1 plus r2 is our new r2. And that will give us, well, the first row will be the same, and the second row will be 0. 2 times 3 is 6, so we'll get h minus 6. And then we'll get -2 here. Okay, so this entry in the matrix here is h minus 6. And now we just need to think about what makes this system consistent or inconsistent, and then what that tells us h has to be. So if h was, say, 5, we would get -1, -2 here. And then that would mean that x2 is 2. It's positive 2, because you would just divide both sides by -1, or multiply by -1. Okay, so if h is 5, that's fine. There's no problem here. We'll have x2 equals some number, and then we can plug that into the first equation and get x1 equals some number. So it'll be both consistent and unique. However, if h is 6, we'll have 0, 0, -2, which is equivalent to the equation 0 equals -2, and that's a problem because 0 is not -2. So that makes the system inconsistent. So really, h can be anything it wants to be other than 6, because if h is 6, then we're going to have an equation that doesn't make sense. We'll have a 0 equals -2 equation. So this system is inconsistent. Oops. If h is 6, because then we'll have 0, we'll get 0 equals -2, and it's consistent if h is not 6, because then we'll have some number here times x2 equals -2, and that can be solved because you can just divide by that number. All right, so you'll see that inconsistency happens when we have this row, a row where we have a bunch of zeros and then a number, and we'll talk more about that, that property next time.